Alright, thanks for coming. So today we are pleased to have Zixiang Xu to talk about degenerate graph. Yes.
Okay, thank you. Actually, I wanted to use the slides, but one day Nika came to my office when I was preparing my slides, and he said, "Okay, man, why did you use the slides? Why not just write on the blackboard?" So Nika is not here. Okay, so I just follow his suggestion, but let's see whether he will use slides in next week. Okay. So when I received the Professor Ong's email in August, I just submitted another abstract of the talk in the Guangzhou, and so I think it's better to give some different talk, and at that time I hope some ongoing project on Turán problem will finish on September, but I didn't. So today I will mainly focus on the constructions in Turán problems, and I will introduce introduce ideas from the random and algebraic constructions, and introduce some of my previous work inspired and motivated by this construction. And if time is enough, I will introduce you a variety of new extremal problems, which I think is very close to the Turán problem. Okay. So Turán problem maybe. Okay. I am a little bit nervous because there are many experts sitting here on the Turán problem. Okay. So usually we use this notation, and it means the maximum number of edges in an vertex and edge-free graphs. So sometimes the objects can be graphs or hypergraphs or some geometric objects, and otherwise, and sometimes the forbidden patterns can be single graph, a family of graphs, and some patterns you want. So original result is from more than 100 years ago, and Mental proved that the maximum number of triangle-free graphs like this, and then this was generalized by Turán, and from the triangle to any small cliques. And a fundamental result in Turán problem is the Erdős-Stone-Simonovits Theorem, which states that for any graph H, the Turán number can be write as 1 minus H 1. So we can see that if the chromatic number of the graph H, so usually when we talk about the Turán problem, the H is of constant size. Okay. And if the H has chromatic number larger at least 3, then we can asymptotically determine this function. But if chi h equals 2, then we only know that the little o n squared. So So it's very important to study the Turán number of the bipartite graph. This chromatic number is 2. So and usually people like to call this problem as degenerate Turán problem. And yeah. So as every bipartite graph is a subgraph of complete bipartite graph. Yeah, because H is of constant size, so H must be a subgraph of KST, and so it's very natural to study the Turán number of the complete bipartite graph. In 1954, the Dwyer and Schultz and Turán they wrote a very general upper bound. I write it a little bit detailed. Yes. And the proof is simple. We just one of the proof we just need to double count the number of the KS1, the star with the S leaves. On one hand, as any n vertex has at most t minus 1 common neighbors, right? So this at most, and choose 2 t minus 1, and you also can count in another way, that is run over all of the vertex and degree, and choose S degree V. So in this part, you can use the convexity of this function, and there will be something like this. Like sum of the degree is roughly the 2 times. Okay, and then you can obtain the upper bound like this. Right? This form. So it's natural to ask. It's natural to ask whether this upper bound is tight. Okay, in general. So this conjecture, we hope that it is tight, and conjecture and for t. So it suffers to prove that when t equals s. So so if we want to show that this bound is tight, we need to show the lower bound. So in Turán problem, the lower bound usually has if we want to show the lower bound, the first way is that use the probabilistic method. That means you show the existence of, for example, KST free graph exists, and then count the number of edges, right? Okay, I did not write down, but I just sketched the idea. For example, you can start with some random graph and count the expected number of edges and expected number of the bad structures. The bad structures usually means the bad structures will induce the forbidden patterns. Okay. So in random graphs, you can count the expected number of the bad structures. Okay. So then you can delete one vertex from each bad structure. Okay. And then so the resulting graph is the H free or KST free. And then you need to check that the remaining vertex is enough, and the remaining edges is the number of edges is enough. So this usually the random or probabilistic method. And there are also some algebraic construction. Okay, so the algebraic construction, or sometimes we see the explicit construction, you can directly tell people that what is the graph look like. Okay, so usually we need some geometry object and the vertex that usually is the geometric objects like the points, like lines in some plane or some high dimension space, and the edge set is determined by some algebraic relation, a sequence or a series of equations. So I give you an example. For example, to prove that the height. Okay, we just consider the two-dimensional vector space of Fp and delete the array. Sorry. Okay, and two vertex, for example, say A, B, and X, Y are adjacent in this graph. And they are adjacent if ax times by is 1 p. Okay, then we can see every pair of vertex cannot have two common neighbors under this construction, and that means this graph is K223, and then every graph has either p neighbors or p minus 1 neighbors because it may contain some loop. Okay, so p or p minus 1. So totally there are so many edges. So that's a very simple construction, and this construction also can be generalized to K3. Yeah, a little bit complicated form like a minus x squared plus b minus y of the triple plus c minus d, because some carefully chosen the element in Fp. Okay, so but this construction cannot directly generalized to the K443. Okay, so the Turán number of the K443 is one of the most challenging problem in this area. Okay, and nowadays many people conjecture that the bond is not tight. Yeah. Okay, but no one knows. Okay. And it's algebra. Oh, okay. Also, there's a very famous conjecture by Long and Cora and Sabo. They use the norm graph or projective norm graph. There's a result I just write down. When t is larger than s minus 1 factor s minus 1 plus 1, and this bond is asymptotically tight. Okay. So this is the algebraic construction. And today I will mainly introduce you some of the random, mixed, random, and algebraic. And this is proposed by the Boris book. I will introduce something about this method and yeah. Okay, so I just have a few comments on these three methods. The first that for any graph H, you can use the probabilistic method to obtain the lower bound of the Turán number, like this form. but it's not good in general. At least for many special cases. Okay, so yeah, so why the project, no, why the probabilistic method usually, for example, if we want to show use the random construction, we can try, for example, P equals N S N. Okay, and this is the probability, and okay, just write the future. Both parts of size n, and we can any two vertex are adjacent with probability p and independently and uniformly at random. Okay, and so it's easy to see that the expected number of edges in this random graph is roughly n minus. That is what we want. Okay, but next we need to bound the probability. We hope that as we want to that the G is KST free, right? So we hope that this probability tends to 0. Okay. So we can we just choose some, for example, for some U and with S vertex. And okay, also the number of edges in the random graph are binomially distributed. Okay, so the number of edges, at least this number with probability tends to 1, are very large. So for any fixed S vertex, we hope that the NU will descend okay, sorry. We want to upper bound the number of these. Okay. Right. Okay, we want to upper bound the for any vertex, for any sequence of S vertex, we want to bound the common neighbor larger than is at least some t. Okay, so and moreover we want to okay yeah, for any vertex V belongs, the probability that the vertex V belongs to the common neighbor of U is P to S, right? Because it's a random graph with probability P and yeah, is n over 1 over n. So the NU, that means the NU obeys the binomial distribution n over 1 over n. Okay. So this tends to Poisson distribution, and this probability can be bounded by t fractional t 1 over fractional t. Okay. Factorial t. Okay. So okay, then use this we can bound this term as all of the subsets of size S nu larger than t. Yeah. Okay. So it's easy to show that the n choose s t square is factorial this tends to 0. Okay.
Probably you want to say the expected number of KST on the left hand side, no?
Yeah.
Here you write the probability.
Yeah. Here we just write the probability and okay.
Yeah, then it's not equal to the sum.
Oh.
Oh.
The sum should be the
Oh, sorry.
expected number.
Okay.
Sorry.
Right.
Okay. Sorry. Okay. Yeah. Sorry.
Number of subtypes I saw big things.
Yeah. Oh, sorry. Number of the. You can just remove this. Okay. So
It's still not true.
yeah. So we hope this tends to 0. So it requires that t is roughly, for example, log n over log n. Okay. Times some c. Okay. That means t.
I think you better use probability, but then upper bounded by the sum of the probabilities. Since now with the expectation it's still not true, since if
Yeah,
you have t plus 1 neighbors, you have multiple KSTs. Since
Oh, so maybe it's a number of S vertices that has at least T common neighbors. or something.
No, this is a probability. Sorry, it's
Right.
still the probability because we sum of all of this. Maybe this is not equal.
Yeah.
Like this. Okay.
Ah.
Okay, this is makes sense. Sorry. Okay. And yeah, so the problem is that you can see the mean or see the expected number of the common neighbor of u is not large, right? It's just 1, right? But if we see the distribution, right here, if we see the distribution, it has a very smooth decay the type, right? And long. Okay, so this part makes us give us a worse control of the probability. Okay, so this distribution is smooth if you only take the random graph here. Okay.
Sorry, what's the x-axis means in that case?
What?
In
Sorry.
the graph?
What is x-axis and what y-axis?
We can see the x-axis and u, right, and the probability. Let me see what's the y. Use what? Yeah, I need to think. And yeah, I just give some feeling that I mean just means the number of u, number of the set u, such that the common neighbor is large, it's very small. Yeah, but the distribution is very smooth and has a long time. So usually, if we just directly take a random graph, we cannot give a better control of the total when we use this, because the distribution is this. So instead we want to find some non-smoothie distribution. Okay, so yeah, this original motivation of the random algebra method. So it's right here. Okay. So the random algebra method, the graph is based on some algebraic objects. That means usually we want to work in the the higher dimension of the finite field. Okay, so the graph usually defined based on the high S dimension of the finite field, and the age set is determined by U and V. We can write as bigg. Okay, so U and V are adjacent if and only if, sorry, maybe just if they are vanished by some random polynomial, bounded degree random polynomial. I just bounded degree. Okay. So that means we can fix some degree d and randomly choose random at uniform at random choose some polynomial, and any pair of vectors in this space, they are adjacent in the graph G if they have vanished. Okay. So okay. So just this is the construction, and then I need to use 3 lemma without proof and convince you that this construction works. The first two lemmas just want to say this graph behaves like random graph in some sense. Yeah.
So can you not move that out because of in the internet? The camera will be watching the other.
Oh yeah, you mean I do not want.
Don't go there.
Okay, sorry. Okay, sorry.
Sorry for it.
It's okay.
Oh, everyone. Okay. So the first lemma is that for each distinct pair of vertex, this graph G, sorry, VG, the probability that they are adjacent is 1 over Q. Yeah. Okay. This means okay. You can see the totally possible value of the function is just Q. Okay. So the possible number of the function is Q, and it's just the very uniform distribution. So that means the expected number of this construction of this graph is n squared over Q.
Okay. What is Q? Would you remind me? Oh.
Prime power. Okay. So yeah, usually we can in this construction, the number of vertex is roughly Q to S, and we hope the S is a fixed number, and in the KST it's just the same as in the KST-free construction, and Q usually goes to infinity. Okay. So the first lemma means that it behaves like a random graph. Yeah, because the number of the expected number of the edges can be calculated like the random graph. Okay.
That is n to the s?
N squared is Q over Q.
Yeah, n squared over Q because okay.
Oh, what is n, right?
Okay. So.
No, n is
the
N is 2 to the s.
n is 2 to this.
Okay,
right?
I completely.
Okay.
Thank you.
Sorry.
Oh well. Isn't it random bipartite graph or is it a bipartite?
Oh yeah. Yeah. It can be bipartite if yeah we just okay we just construction like this. Okay.
Union maybe?
No, not union. Okay. Yeah, and yeah. So the second lemma tells that it's so that it behaves like a random graph when we count some small patterns. Okay. Under some condition, for example, if R there's 2 parameters and if R and S less than the minimum, usually the constant T is less than the Q. Okay, and then if there is a subset, we write this as X, this as Y, and if L in X and is a subset of X and R is a subset of Y and L of size R and L of size S and R, then they form a complete bipartite graph. The probability that they form a complete bipartite graph is also like the random graph. Okay, so the probability that all of them, I just write simply K. Let me think. Oh, I just use a polynomial and FUV for O. U in L and V in. Okay. S Q S times R 1 over Q to S times R. Okay. That means for some very small patterns, the probability that they appears in the graph G still like the probability in the random graph. Okay. So the third one is the most important part in the in this method. That means we need to briefly introduce some very simple concept as just right here. So when we apply the random algebra construction, we want to we want to describe the common structures. Like if we fix the S vertex, then they are common neighbors as a variety, algebraic variety. Okay. Usually, you can simply regard it as common zeros of many polynomials. Okay. For F1, yes, right is like 1. Fs. Just like the common set of common zeros. So the third lemma tells that the variety we usually call the language bound, and let me see the condition. Okay. For every number of the polynomials S and the bounded degree, degree D, there exists some constant C, such that if W is a variety of then the size of the W either is very small, it's bounded by some constant, either it's very, very large. So, or very large. This constant C and so actually this one the dimension of H is 0. This is 0, and this is larger than 1. Okay, so that means the either very bounded by some constant, either is very large. So actually, this formula can be there's a more accurate form, and we just need this. Okay. Well, that means it's either very large or very small, and we will see this. We will use this very important.
What did you write? Did you write W is bigger than Q minus C?
Yeah, Q minus C times some error term.
Is it the same C? Or?
Yeah, the same C. Okay. But actually, for this part, there can be there are more stronger result. Yeah. Actually, for example, there can be some dimension like this, but this is enough for our purpose. Okay.
And small d is the upper bound on the degree.
Yeah, if the dimension of the variety is 0, dimension means you need to define some sequence and like this and the minimum number of the elements in the subset in the line. And but I do not introduce this. We just need to know that either bounded by some constant. The C is depends on the number of polynomials, and the degree of the polynomials.
Okay.
Just these two numbers. And either it will depend on the Q, and the Q is very large. Q is sufficiently large. So okay. So yeah. So to use this method, next I just simply sketch the how to use this method to bound the and sorry, I just like this form. Okay, we just use about construction. And the vertex set is FQ2S union of FQ2S, and the edge set is we can uniformly at random pick some bounded degree polynomial. The D should be carefully choose. Yeah. In this construction, I remember D is roughly S squared or some larger than S squared, just enough. Okay. Okay, so once the random graph or the random algebra graph is formed, then it's easy to come to the expected number of the edges as we have mentioned. Yeah, the expected number is like this. I do not write down.
Shouldn't there be some condition on D, like lower bound on D or something? Like
No, there's nothing about D here. So D is the
no, I'm saying like for the construction, like it's probably not meant for all HT, right? Like you need some lower bound on T, right?
T.
Yeah.
Right.
T, like, or is it?
there's no and I do not write the accurate form of the T, right?
Ah, okay.
Later I will, yeah.
Okay.
In this formula, the T should be related to the D. Right? Later maybe we will give some. We will discuss about the how large of the T. Okay. So we just a simple sketch the proof. Okay. So as usual, we hope to fix as vertex U1 US, and we also want to write this U, and over to bound upper bound is common neighbors, right? But directly upper bound is not easy, so we can try to bound this. Okay. The D is similar as I just write. Maybe it's not correct, but like this form. Okay, and do not ever just like this form. It's a little bit larger than S squared. So what this means? This formula is maybe not exactly, but it comes to the number of all possible. For example, if we fix some ks1, this x vertex, and ks1, and this formula roughly counts the number of all possible number of the when we put d stars together. Okay, that means there will be a large collection consists of ks1, ks2, and ksd, right? So this formula roughly counts the all of possible of the elements in this collection, because there will be some degenerate. You have some say is it together? Put it together. So right. Okay. So we just want to upper bound this because I just write here. The reason is that when we want to bound the probability that the common neighbor or the probability that the size of common neighbors of U larger than T, we can rather than the probability of this, we can rather than bound like this T2. Okay, this is the same. Okay, so but counting this, it will be helpful. Yeah. Okay. So how to upbound this? We just mentioned that it roughly counts the number of all possible elements in this collection. Just roughly, maybe not exactly.
What is that collection once more?
Yeah, we put d many ks1 together. We fixed the S vertex. Yeah, and this just roughly counts the. Yeah, there may be some conflict. Yeah. So element in this.
So combinatorially,
Yeah.
you fix the set U of S vertices combinatorially, he's counting the order B tuple
Yeah.
of common neighbors of U. But probabilistically, if you view n of U as a random variable, he's trying to bound the nth moment with this random variable.
Okay. So for each member P in this collection, the possible number is at most can be upper bounded by the unfixed number n to the unfixed number. That means P minus S, right? At most. Okay, because the number of unfixed vertex is just P minus S. Okay, this is okay. And on the other hand, we can see the for each member in this collection, the number of edges is S times P minus S. Okay, this is complete bipartite graphs. So we can use the second lemma.
Oh, and are we still on a random bipartite graph or are we on a random graph?
Yeah, now we are in the construction of the above graph, random algebra graph. Okay.
Yes. So.
Yeah, but we just count the for each element P. P is cast 1 or cast 2 or cast D, and all of the possible number can be bounded by the n to its unfixed number of vertex. So you can see for there's S vertex and there's some number, and the total number is P minus S is the unfixed number. So the number of is at most like this. Okay. We just count the all possible this configuration or these subgraphs. Okay. So the second lemma tells that the probability that some member appears in this random algebra graph is behavior like the random graph. Okay, that means for any P, in this collection. It appears in this graph. So P appear in this graph. The probability is Q2 minus and 1 over Q to it's the number of the edges in P, right? Okay, so we can put it together. That means the probability, the expected number of, we can sum over all the member in the collection K, and this number and P minus S times Q2 and sum of it together, and then this is exactly it's bounded by some constant. Okay, because you can see this is S P minus S. Okay, and Q to the S is maybe not. Yeah, Q to the S just the n, and the times and this just the constant. Okay. N is Q to S, and they together just the constant. Okay. So. So in this argument we use the second lemma, that the probability of some that some small patterns appears in the random algebra graph is behave like this probability in the random graph. Okay, so the final step is it's very important. We just fix S vertex, right? So we can write all of the unfixed vertex as a variety. That means for any x, if he is in the if he is the common neighbor of the set U, then it satisfies f U1 x equals 0 f US x equals 0, right? So now you can write these S polynomials as distinct S polynomials on one variable x. Okay. So we can apply the third lemma. The third lemma means that the W either is at most constant or larger than, you can see the Q over 2. Okay. So why is helpful? Because the probability or the distribution is not smooth again. Okay. Because so a key step is that now we want to bound the probability, means W. This is a key step. By this, we can see the probability that W is at least capital C plus 1 is equal to the probability that W is larger than Q over 2. Okay, so this is the same. Yeah, and and this is what this we can all of the put the D. The W is the NU actually, as we have discussed about W is NU. So we have known that the expected number of this term is bigger 1, right? So we can use the Markov inequality to upbound this probability. That is the big O1 or Q2D. So now we can see the advantage of this construction. If we just use the random construction to upbound this term, right? If we directly use the Markov inequality, then this is just a constant 2D, right? But the random algebra, this lemma tells, especially the third lemma, tells us that we can have a better control of this probability. Okay. This probability is very important because this formula is very important. Yeah. This observation actually. If it's larger than some larger constant, then it must larger than, or at least some very, very large related to the Q. Okay. So yeah. So the following steps is very standard because the probability is very small. So we just remove, we just calculate the expected number of the beta structure. I mean the expected number of the C+1, and it's easy to upper bound. And then we just destroy the beta structure, and we can obtain the result we require. Okay, this is and this is key ideas. So that means sometimes when we just use a purely random or purely probabilistic method, and we just can use some union bound or some, I mean the worst control of the probability. But if you put some, or you define it in some algebraic objects, then you may have some better control of the probability or the expected number. Okay. So yeah, time is not enough. But I just want to mention some motivated by this work, this idea. The first thing I want to mention is that the lemma 3, as someone proposed, the constant C is very large. So usually, maybe not exactly, usually the constant C should be the product of the degree of every polynomials, maybe larger enough, maybe larger, even larger. For example, if D2, yeah, it's needed to the product form, so it's very, very large. For example, the one in the KST-free case, the T should be, I remember it's larger than TS to 4S. It's worse than the bound on the norm graph or projective norm graph. It's S. Okay. But recently, book also developed new ideas and even improved the constant dependence in the projective norm graph. But this is his original result like this. Okay, this is a comment. So there's two questions. There are two questions we can further study. The first, we care about the dependence. That means we can setting that if the n is sufficiently in terms of the t, and the t is also sufficiently in terms of s. Okay, we can study the behavior of the large constant t because this method requires the t to be very large, right? So we can. So this setting, under this setting, I prove that actually the random algebra gives the bound like this. That means C, S, T, N to like this. Right? The constant depends on S and T. So one of my previous work proved that we can write it as like this. Okay. So this is very coincidence. It matches the bounds of KST bound When t is large, means this term. Okay. So it's the same. Okay. So this is the first motivation because this constant is very large. So we can also study the dependent or the asymptotic behavior of this very large constant. Yeah, we can also regard it as a constant. Okay. So the second is that once for some structure or some graph pad, some graphs, some hypergraphs, we know we can use the random algebraic method to give some tight bound, but the constant is not good, right? Not good enough because the constant is very huge. Okay, can we give some algebra construction or explicit construction to improve the constant dependence? Okay, we make some. We try to learn some structures. For example, one of the is for one subdivision of the complete bipartite graphs, like the S equals 3, and usually if we just use the original random algebraic method, this constant t is very, very large. For example, larger than 10 through 10 is very large number, but we can reduce it to roughly 20 or 25. Okay, it suffers, but it's still we do not think it's good enough, but it's significantly reduced. Discrete this number, and for some other there are also some problems sharing the common motivations that I have studied. Yeah, and okay, yeah. So yeah, I think time is okay. So I will just finish here. Okay, thank you.
Okay, questions?
Can I ask a question? So to get the correct power on the t, like for that result, t to the power 1 over s. No, up there. Yeah, that one. Yeah, to get that, you used the exact same random algebraic construction and analyzed it like more carefully, or did you use something?
Okay, I just use a trick.
Okay.
This trick comes from the so-called the tensor power trick. Usually use the additive combinatorics and some geometry problem. We can, roughly speaking, we can put many such random algebraic graph together, and then it maybe forms a multi-graph. The edges maybe not single; it's multi-graph. And then when we delete the vertex, we also delete the vertex. We also delete all of the multiple edges. So if we can control the number of the multiple edges, and then delete all of them, and the remaining is like this. So it's like we put many the random algebra graph together, like they use the similar ideas in the tensor power trick. Just like actually we do not only work. So this trick does not only works on the complete bipartite graph, but also can be used to some complete apartite uniform hypergraph and some like theta graph and some other structures which have been applied as a random algebra method. Okay, thank you.
Other questions? Okay, for now, let's thank the speaker.